My processor want to receive something from an input device. In that particular case, this I/O interface acts like a input interface. This I/O interface receives the data from I/O device end with the help of data lines PA0 to PA7. So whatever the data it receives from external input device, that was copied onto this data in register only when this was enabled. So that is enabled by this signal CA. So how your processor accesses the data from an external device? In that case, what actually your processor can do in previous occasion, that is, whenever our processor want to send something to an output device, first our processor generate an address of it, later it will activate a control signal, later it will activate as an asynchronous signal, which is a handshaking signal, master ready. At the same time, it will place the data on data lines. That's what it do. But now if I want to receive a data from an input device, the first thing what a processor can do is it will generate an address. That address can be received by this particular I/O interface with the help of address lines A2 to A31, which is a 30-bit address. So then this will decode that address, and it will activate only one at output of a decoder, which is logic 1. That is given to these are 3 and gates 1, 2, 3. So this one is applied here, here, and then here. So this is, and next what it does, it will generate a control signal, which is a read or write. So here our operation is receive something from an input device, so it will activate a read signal. So this r/w bar becomes logic 1, because r/w bar, which indicates read/write bar. If the signal is 1, that is belongs to read operation. If it is equal to 0, that was belongs to write operation. So here operation is a read, so this signal must be set to 1. If it is 1, then this is applied here, this is 1, and again it is applied here, it is 1. Then the output of this inverter becomes 0, then this input of AND gate is equal to 0. So at this moment it is very clear, friends, that is, irrespective of our remaining inputs of AND gate 3, it will produce as logic 0 at output, because there is one of the input is equal to 0. If it is happens to AND gate produces the logic 0 at output, then automatically it disables this data out register. Not only that, so here one more thing is the same signal is given to this is becomes 0, and at the same time it is also goes to this is equal to 0, like this it can happen. It is one thing is clear, this AND gate output is 0. What are the remaining inputs for this? The third input for this, the 2 AND gates or 3 AND gates, is master ready. We know that a master ready signal is generated by the processor. It will inform to the I/O interface as well as the external device that our processor is ready to participate in data transfer. So this master ready is set to 1. If it is 1, this input is 1 and this input is 1. Fine. Now important thing is the outputs of gate 1 and 2 are purely depends on the remaining 2 inputs. In order to receive a data from that, here this driver circuit must be active. When this driver circuit is active, the driver circuit is active only when AND gate 2 output becomes 1. When AND gate 2 produces logic 1, these are 2 inputs are set to 1 and 1. What those 2 inputs are? This is one of the input, that means A0 is equal to 1. And second, this is equivalent to 1, that means here it is 1. The inverter input must be 0, that means A1 is equal to 0. So it is a very clear, friends, A1, A0. If these are 2 are set to 0, 1, I am going to read data from an external device through this data in register and this driver circuit. So if these are 2 are set to 0, 1, what happens? Coming to the next case, if it is a 1, then it is becomes 0. It is a 0. This 0 is applied here. So irrespective of other input, output of AND gate 0 is equal to 0. AND gate 1 equal to 0. Once it is 0, then what happens? If it is 0, then only you can go for AND gate 2. If this AND gate 2 is set to 1, this driver circuit is active and it is ready to receive data from data in register. So like that, our processor receives the data from an external device. With the help of this PA0 to PA7 lines, data in register and this particular one. And next important thing is, whenever if I want to receive the status information of these external devices, that I receive with the help of this SIN as well as SOUT, these two are present in status register. I select the status register with the help of this A1 and A0. If I make both are 0, 0, I can go and select my status register. I am already clear told you at the beginning of this concept, with the help of A1 and A0, I am going to address 3 registers which are present internal to this. One is that is a data out register, second one is a data in register, and third one is status register. With the help of this I/O interface, our processor can communicating with either input device or an output device. Our processor can communicating with an input device with the help of a line set PA0 to PA7, and it can communicating with an output device with the help of PB0 to PB7, and CB1 and CB2 are the handshaking signals which are helpful to us to communicating with an external devices. So in this case, I have a disadvantage. What the particular disadvantage is? Instead of using a common bus between an external device and I/O interface, here we are using 2 different buses. One is for to receive a data from an input device, that is a PA0 to PA7, and another one is to transfer a data to an external device through the help of PB0 to PB7. Here we are using 2 different buses. So now we are going to discuss the general parallel port, or an I/O interface. In that case, I can go and use only a common signals. With the help of that, I can transfer the data or I can receive the data to or from an external devices with the help of only a common signals or a group of signals. So that is this particular one. See here friends, with the help of this PA0 to PA7, which are bidirectional lines, with the help of that, my processor can transfer the data to an external device. With the help of these lines, I transfer the data to this, as well as I can receive the data from that side, that is I can receive the data from an input device, again with the help of the same lines through this particular path. So we can go and discuss something regarding to this particular interface circuit, which is our general purpose parallel interface. So the difference between this and previous one is, in previous one we have 2 separate data lines are exist between an I/O devices and your I/O interface. But now we are using common signals. So whenever my processor want to transfer something to an output device, that case it plays data over these lines. Now the data is given to the input of this data out register. Later the data is transferred to this driver circuit. From that it is transferred to an output device. This is the way. This is the way the data was transferred. And second thing, if I want to receive the data from an input device through this interfacing circuit, that part is like this. It receives the data like this. It is copied onto data in register. That is given to this driver circuit. That is the case now. Data like D0 to D7. Like this, it will collect the data. So here important thing is, we have to go and program these lines. Based on, we are going to communicating with either input device or an output device. According to that, I programmed these lines. For example, if I want to receive something from an external device, which is my input device, that occasion these lines must be inward. And similarly, if my processor want to send something to an output device, that occasion these lines becomes an output lines. These signals can be programmed with the help of a data direction register DDR. Here we have a data direction register DDR, which is an 8-bit register. With the help of this 8-bit register, I program these lines can be act as an input lines or an output lines. Let me assume, friends, that is this data direction register is like this. It is an 8-bit register. This is an 8-bit register. So the bits are like this. This is your DDR. This is bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. I want to use these lines as an input lines. That means I collect something from an input device. So then what I can do is I can go and copy these values are set to 0, 0. That means my processor programmed this data direction register by sending a command word that was copied onto this data direction register. If a data register particular bits are set to 0, no doubt a corresponding signal here is make it as input signal. That means a more clarity about this is this 0 bit is belongs to program PA0. If it is 0, no doubt PA0 is set to input signal. And next bit this is belongs to PA1. Next bit this is belongs to PA2, and so on. This is belongs to PA7. If any bit in this data direction register is set to 0, that indicates that the corresponding signal here is defined as an input signal. If I take the reverse, that means this bit is set to 1. Then what happens is this PA0 is set to an output signal. That instant your processor want to send something to an output device. So here this data direction register plays an important role to us. So first you have to program this data direction register to define the direction of these lines, and later we define our operation is a read or writes. So if our operation is read, then we collect the data from an external device through this data in and driver circuit. It will collect with the help of data lines T0 to D7. If I want to transfer data to an output device, that occasion it will transfer data. First it placed on these data lines that was copied on data out register. Later it goes to driver circuit, and from that it is transferred to an external device with the help of a PA0 to PA7. And here this is an important thing, a register selection signals are present. Generally here I have three signals, RS0, RS1 and RS2. RS represents register select. I have three signals. With the help of those three signals I can go and select 8 different registers which are present in this I/O interface circuit, which may be data in register, data out register, status registers. And to selection of all these things, we took the help of this register selection input signals, that is RS0, RS1 and RS2. And next we have a control signal which is R/W bar, which is a read/write bar. And here these are the two signals, one is a ready and accept. Generally these are two signals are treated as master ready as well as slave ready. So in this the two signals, ready signal is act as a master ready signal. This is act as a master ready, and the next one is accept. It can be act as a slave ready signal. These are two other handshaking signals. Apart from this, we have two more signals. One is my address. So before our processor want to communicating with any particular device, what it do is it will generate an address. So that address we have placed on this my address lines. And next important one is we have an interrupt signal. So that is your I/O interface also send an interrupt signal to the processor, right? So here the C1 and C2, these are two becoming as handshaking signals to communicating with our external device by this I/O interface. So like this, this particular interface circuit is the best one to communicating with an external devices by your processor with the help of only a set of lines. But in the previous case, we have two sets of lines, one set of line for to receive a data and another set of lines for transfer of a data. So this is about our general purpose parallel interface. I hope you understand this what this is. And next we shifted to the second variety of interfacing, that is serial interface or a serial port. So basically we have two types of ports, one is a parallel port and second one is a serial port. So now we are going to discuss about serial. It is used to connect an I/O devices to processor which it transfers or receives data bit by bit. Yesterday I clearly told you that with the help of a serial port, with the help of a single line connector, our I/O interface transfer the data to an external device bit by bit, or it can collect the data from an external device bit by bit. So for connection of an external device which knows only serial communication, definitely your I/O interface must have a serial port. So that is the first one. The serial port communicates in serial form in I/O devices side and parallel form in processor side. There is no doubt. Because always our processor can communicating with either memory or with an I/O module. It is purely in parallel form. But coming to I/O devices case, we have some type of I/O devices are the parallel devices and some of them are the serial devices. So that once your device was a serial device, then your I/O interface can communicating with that external device in serial form, but it will communicating with the processor in parallel form. There is no doubt at all. So that is the meaning of this. The transformation between the parallel and serial formats is achieved with shift registers. Absolutely. That means here my interface circuit must have a shift registers. Their job is they convert the received data which is in parallel form to serial form. Once your processor wants to send something to an external device which only knows a serial communication. And another end is if the processor wants to receive the data from an external device which only knows a serial communication, it collects the data in serial form. Later that shift register converts into parallel form. So that the transformation that is from parallel to serial or serial to parallel, we need a shift registers. Those shift registers must be present in this I/O interface. So that's the meaning of this. The shift registers are present in the I/O interface circuit. That's what I'm saying. So this is a block diagram of a serial port. So see here friends, let you can assume this end I have some input device. Here I have an input device. The input device will transfer the data to I/O interface with the help of this serial input. And similarly here I have an output device. With the help of the serial out, my interfacing circuit transfer the data to an external device in serial form. So this is the whole interfacing circuit. See here friends, for example, my processor want to transfer the data to an external device. That is the case 1. Processor to external device, data transfer. So here the external device only knows serial communication. So this is the case. Then what your processor first can do? It gives an address by using my address. It gives an address of the corresponding device, and later it will issue a control signal that was write. This is set to 0. And your processor is willing to transfer the data, so it will activate master ready. So that master ready signal here is act as a ready signal. It is also set to 1. Then it places data over these lines. Now the data can be received by this data out register. It can be placed here. And the data is parallelly applied to out shift register. So here data out register data was placed onto this out shift register. Now it is the responsibility of this out shift register. It converts the data which is in parallel form to serial form. That means at the output of this shift register I have a serial out signal. With the help of this, our interfacing circuit transfer the data to an output device. So this output shift register converts data from parallel to serial. So output shift register, what it do is it will convert data from parallel to serial. Fine. Like this it will transfer the data. The case number 2 is if my processor receives the data from a device. Processor receives the data from a device which is again is serial. So if a processor want to receive the data from an external device, again it will place an address and it will activate now the read signal. So this R/W bar is makes 1 and it is ready to participate in data transfer. So ready signal is set to 1. Right, like this. These signals are set to 1, 1, 1. Then it receives the data from an external device by your I/O interface with the help of this serial input. It means your I/O interface collects bit by bit from an input device. The data was copied on the input shift register. Once it receives all the bits from an input device, for example, I collect the data in terms of bytes. That means if I receive successfully 8 bits from an input device, let me mention that is one of the frame or data bytes. Later that byte is converted into parallel form by this input shift register. In previous case, output shift register, what it do is, it will convert data from parallel to serial. Now this input shift register do a reverse task. That means it will convert the data which is in serial to parallel. Once it will convert data into parallel, that was copied onto data in register. Later that is placed onto this driver circuit. From that it was placed onto the data lines. So like this, our processor can communicating with the external devices which knows a serial communication with the help of this serial port. And here also the same thing here, RS1 and RS0 both are used for the selection of our registers. I have a data in register as well as data out register along with the status register. For selection of these 3 registers, definitely at least I need 2 register selection bits. That's why here I have 2 signals. One is RS1 and RS0. And once your operation is successfully performed, then what happens is it will send an interrupt signal. So that is about this. And here there are 2 important things, that is a receiver clock as well as transmitter clock. What is the use of this? Let me get one discuss about it. The input shift register can start receiving another set of 8 bits from the input device after loading the contents to data in before the processor reads the content of data in. This is called doubling buffering. What's the meaning of this? See here friends, once your external device sends the data to this input shift register, it copies the data and that is converted to parallel form. It will transfer the data to this data in register. Before this data can be received by the processor with the help of this driver circuit, one more data byte was received by this input shift register from an external device. That particular incident, what we can call is double buffering, because already previous received data was copied onto data in register. The data still not received by the processor or not collected by the processor. Meanwhile, your I/O interface collect one more byte from an external device in serial form that was copied onto input buffer register. So this particular thing, what we can call is doubling buffering. So that is important. And next important thing is the speed of transmission of data over serial interface is known as bit rate. So how fast we are transferring or how fast we are receiving the data bits, that we referred here as bit rate. Generally this bit rate depends on the nature of devices we are connecting, because some of the devices can operate at faster rates. That means some of the devices they can transfer or receive data at faster rates, and some of the devices they can receive or transfer data at slower rates. So this bit rate depends on the nature of the device which you are connecting to our interface circuit. So that is, in order to accommodate the devices with a range of speeds, the serial interface must be able to use a range of clock speeds. Because some device with some speed can transfer, or a device can receive with some speed. The speed of operation is purely depends on the clock signal. So, if I want to connect or accommodate different speeds of interfacing devices or different speeds of I/O devices, then what your interfacing circuit must have is, it must be able to use a range of clock speeds. I hope you understand what's the use of this. If you go for previous slides, see here, so this is a receiving clock that indicates at what speed our I/O interface gather the receiving data from an external device. That is purely depends on how fast the external device transfer the data to I/O interface. That is purely deciding on this receiving clock. And similarly, if your processor want to transfer something to an output device in serial form, in that case, how far the external device collects the data from this interfacing circuit, that is depends on transmission clock. So this transmission clock decides the bit rates in both the receiving operation as well as transfer operation. So that is the meaning of this particular one is. And next we have several standard serial interface circuits. In that we are talking about only 2. One is UART, means universal asynchronous receiver and a transmitter. It is preferably for low speed serial devices. The devices which are operated at lower speeds, If I want to connect those things to our computer system bus, then we are using an interface circuit bus, that is UART, means universal asynchronous receiver and transmitter. And one more variety of that type of standard is RS-232C. This is for connection to communication links. That means here we are using data rates of devices which are somewhat faster. Those cases we are using this particular one. So like this, there are two different standard interfaces we have. One is UART and second one is QART. I hope you understand the concept of I/O interfacing circuits. Basically, we have two. One is a parallel ports and second one is a serial ports. In the parallel port, we discussed first how we are connecting an input device to our processor with the help of input interface. Later, we discussed about how we are connecting an output device to processor with the help of output interface. And later today we discussed about a common interface circuit which can connect both input device as well as output device, but we are using two separate buses. But coming to generalized case, the parallel port, we have only a common lines. With the help of that, we can transfer or receive our data to or from our devices. And later we discussed about our serial communication. So this is about I/O interface circuits. In the next class, we will discuss about some other topic regarding to the buses. Thank you for patiently listening.